opportunity to give this talk. So this will be my updated talk from SNI. This joint work with Josef, who's here. And it's related to solving partial differential equations which have origin in differential geometry and mathematical physics. So here's the plan of my talk. So first the motivation, then I will talk about Poincare lemma, which is one of the few tools to solve partial differential equations in differential geometry. The other one is Frobenius theorem, and there is also analytic say theorem, which is called Cartan-Haller theorem, which is I think the most sophisticated. But I will focus on the methods which originates from the Poincare lemma. Then I will say more about covariant exterior derivative and parallel transport equation, which is one of the simplest equations in differential geometry, which can be solved using these methods. And then I will say something about other applications which these methods can be applied. Okay, so first the motivation, because this is a school, training school, so let's start from the very basic differential equations. So this is an ordinary differential equation, very easy, and you can solve it using integral. So you simply integrate both sides, and you get that this unknown function is equal to some constant, which is the initial conditions, which is element of the kernel. So the differential operator has non-trivial kernel, that's why it's difficult to inverse it. So that will be our problem in more complicated differential equations. Plus something which is called integral, so it's some kind of inverse to the differential operator, but not fully, because the kernel of this differential operator is non-trivial. Okay, so this more complicated differential equation. Oh, by the way, this differential equation, if we replace derivative with exterior derivative, has the form of something like this. Okay, and we will go back to this later. Then the more complicated equation is like this, and it's this term is much more complicated. So we have now x is equal to f times x, and if we switch to exterior differential equations, then this equation corresponds to d phi, say plus or minus, say plus a times wedge phi is equal to some j. So it's non-homogeneous parallel transport equation. Okay, and if you want to solve this equation, then you have right? Then you have you integrate it again as before, and you get that it's constant, which is initial conditions times integral, but it's not solution because x is also here. So you take this x and put here and again, and you get infinite series. Of course, you have to impose that this series is convergent. So well, it's called Newman series. So there are some well-known methods to check if this is convergent. But generally, you can, for example, assume that this is L2 function. So it has norm of the bounded norm. Okay, but as I said here, maybe there are some analogous methods which can give you the solutions of this differential equations, or equations on geometric origin. And we can solve it, and we can show that this is the case. But you can note that sometimes the solution of differential equations is not in closed form, it's in the form of the infinite power series, or some kind of operator series. By the way, there is also other nice equation, which is of this form. It's called the Riccati equation, and if you say exterior modify it, then you get something like this. So the very close analog to the Riccati equation is the Cartan equation for the curvature, or definition of the curvature for Cartan. Okay, so let's focus on Poincare lemma, which is a way of how to solve this equation. So, yeah, sure.
Can you tell a bit more, because I was thinking in this case it's one-dimensional. So
yeah.
is omega is non-zero?
Once again?
So you work in one-dimensional manifold, right? So omega of H omega is non-zero?
Well, it's generally non-zero.
Because it's one dimension, right?
No,
It's
it's,
only one
well, it's matrix or say the algebra valued form. Yeah. So sorry.
This arrow is generalization or what?
Yeah. It's some kind of analogy. It's not strictly generalization. It's only to show you what is correspondence between simple ODEs and exterior differential equations. But it's only analogy. I will show the exact analogy later when I discuss this Poincare lemma. Okay, so this is the basic Poincare lemma, which means that a cohomology group of open set or Rk is trivial. So every closed form is also exact. But it's not useful in computation. So the more useful way is to, as you know, to use homotopy invariance formula. So we define operator H, which is called homotopy operator, and we have exterior derivative D, and they fulfill these conditions. So this is identity, or pullback along the identity, which is identity, and this is pullback along the constant value. So, well, maybe I will cover this. So homotopy, it's exactly linear homotopy, because there is plenty of homotopy. So the setup is as follows. You have a manifold, you have an open subset which is star-shaped, so there is some kind of central point, call it x0, and you can contract each of the points from this set U on the manifold M to a single point. And you can contract it in many ways, and generally the most useful way is to use this linear homotopy. So you T is parameter along which you contract. So x0 is the center of this set, and S of x0 is the constant map. And you define this Euler vector field, and you plug this Euler vector field into omega. You evaluate the form on this homotopy, and you integrate along T. And that's the way of how you can invert exterior derivative, or at least a bit invert, because D has non-trivial kernel, so we have to deal with this also. And this part is pulled back along this constant map. Okay, so as I said, there is plenty of these homotopies. For example, instead of T here, you can take T square or sine of T or something else. But this linear homotopy is more interesting because it has very nice properties. For example, it has this nilpotent, so H squared is equal to 0. And also, using this and this property, you have that the square of this operator HD is the same as HD, and the square of this operator is the same as this. So if you forget about this part, which is effective only for zero forms, because on non-zero forms it's 0, where action of this operator is 0, then you see that this is the composition of the space. So you have two projectors. The first is this one, the second is this one, and this is the composition of identity operator into these two projections. So what's the images of these two operators? So the first one, I mean this one, is so the image of this one is these are exact forms, because U is star-shaped, so they are also closed. So it's image of DH or the kernel of D. But there is also the second space, which is called anti-exact space. Well, it's module over C infinity, and it's image of HD, and it's kernel of H. Okay, and we have this direct sum decomposition. So on star-shaped set, we can decompose the vector space of these forms into exact part or closed part and anti-exact part. And this is very useful because it's direct sum decomposition. So, for example, why or how we can use it. So let's focus on this first equation, or maybe this one. So we have d alpha is equal to j, and we're looking for alpha. So we take exterior derivative of this, and we get that this constraint dj must be equal to 0. So j must be exact form, yeah, as I said. And of course, because we know what is the projection on the exact part, which is dj, so j is equal to dj, so it's in the image of j, sorry, of the edge. So if we plug this into this equation, we get something like this. So we extract d, and we have alpha minus aj is equal to 0. So alpha minus ij should be exact, because this part in the bracket vanish. Okay, so because of that, alpha differs with hj by some exact part. So c is some kind of constant, but it's exact form, which is in the kernel of the d operator. Okay, I think it's well known. So if you replace d by this and integral by homotopy operator, or other way around, you get this differential equation and this solution, which I showed at the beginning, which is quite similar to this. You have constant here, which is kernel of this operator, and here is exact form, which is kernel of d operator. And you have homotopy operator and integral, which are analogous in some sense. Okay, so now let's focus on something which is called minimal coupling in physics. And there was very nice talk in the morning about this. So assume that if we take d of this equation, we have that dj is not 0. So j is not exact. We can have this. And so because we know that the differential forms decompose into exact and anti-exact parts, so we can decompose this part. And this part which fulfills this sits here. It's anti-exact. So it fulfills this equation, and we assume that it's not 0. So we have that this part will be exact and this will be non-exact. So we don't have any way to compensate this part. So what we can do? Well, we can say that this equation has no solution, or we can try to modify this equation by adding something. And there is plenty of ways of how we can add something. One of the ways is to add some additional term, which consists some additional differential form, which is somehow defined, and try to solve this equation. So, so this is this minimal modification of the derivative, which is called minimal coupling. It's introduced like Cartan would like to introduce it. And by the way, we see also on this example that when this right-hand side, which is describes some interaction between our system and outside world, is anti-exact, then we have to introduce some additional fields or something which compensate this outside interaction on our system. And this outside interaction is described by this additional field, which is called connection. Okay, so let's focus on covariant exterior derivative. So it was topic of many talks today and yesterday. So the setup is as follows: we have some bigger space, and we have some smaller space, and we have projection. So, and we also have this vertical direction. So in local sense, we have a set u times v, and it's contained in the Euclidean space. And we assume that the ones of the set is star-shaped because we want to use Poincare lemma. And we are interested in the differential forms which are valued in this vertical part, or more generally, we can also consider something more like the big space, the base space, and also additional vector space which serves as the space for the values of some forms. So the sections of this whole space can be considered, well, which means that it's described by these red parts, can be described as equivariant base forms, which are denoted by this green part. So this is one-to-one correspondence. It was also mentioned many times here on this school. Okay, so now the operator which acts on these forms, which is somehow invariant with respect to the action of the group, is called covariant exterior derivative, and it has form like exterior derivative plus a wedge something. Okay, and A is one form, which is valued in endomorphism. Well, generally it's valued in Lie algebra, but yeah, generally we can take Lie algebra to the matrix algebra. Okay, and comparing this, we have here this covariant exterior derivative, and it corresponds to the other operator which acts on the sections of this associated vector bundle, which is called covariant derivative. Here are the basic definitions. Okay, anyway, we focus on this equation. Yeah, so first let's focus on the parallel transport equations where we are looking for phi, which is K form, which is valued in the vector space V. Okay, and we have to assume some initial, there is no time, but I call it initial, or boundary condition, dH phi is equal to C. So the exact part of the phi is some other exact form, which is valued in V. Okay, so decompose this solution, which we are trying to find, into two parts. The second part is in the kernel of this, just a moment, of this operator. Here, it's algebraic operator. So let's assume that we can solve this equation. It's not always possible, but well, okay, here it's possible. Later it will be not possible. And using this, if we know this equation, this solution, or at least some kind of form of this, because this not uniquely determine this phi2, we can plug it here, and we have such kind of equation. So this is a covariant exterior derivative acting on phi1 is equal to some exact form here. Okay, so, and also elements which are exact and belongs to the kernel of this A wedge operator, they are called gauge modes, because they you can shift any solution of this this original equation by this gauge mode, and you will get the same solution. So there's no uniqueness. Yep.
So what is the condition? How do you split into phi1 plus phi2?
Well, there is no condition. You assume that only this this is the.
So phi2 equal to 0, right?
Yeah, yeah.
It works.
Yeah, precisely. Yeah, it's non-unique. Yeah, because you know, phi2 equal to 0 is exact, and also it's in the kernel. So it's gauge mode. So now you can shift by the gauge mode as you want. That's non-uniqueness of this solution. Okay. You can also take any constant, and it's the same. It's also gauge mode, but they are also more, say, more solutions that are not gauge modes. You can take any form which is not constant, not in the kernel of D, and it solves this A wedge phi is equal to 0, and it will work. Okay, so how to solve this equation? So, well, if you are a physicist and or you work with differential equations, it's very easy. Just simply use a perturbation series. So, for example, introduce some small parameter lambda, which is a real non-zero parameter, and just assume that your solution is in the form of the power series. So, lambda square, and so on, and just plug it into this and compare all the terms with the same power of lambda. So, at the power of lambda to the 0, so at 1, is d phi 0 is equal to 0. So it says that the phi 0 is arbitrary exact form. Okay, and then the first term is d phi 1 is equal to A wedge phi 0. So this is known, it's arbitrary, but it's exact. And you compute this one, and you go on and on. And finally, if you gather everything, you get the very nice power series solution. So the solution is this operator, homotopy operator, acting on this A wedge operator and to the power of L. So it's L times application of this operator, acting on some arbitrary exact form. Okay, so it's very easy power series solution. So you pick any exact C, you apply this operator, and you get one solution. You take another C, you get another solution, and so on. So that's why I said that C is initial value or boundary value for this problem. Okay, so now what happens if this this equation has non-zero right-hand side? So you have to switch or take two cases. The first one is when j is exact, and the second is when j is arbitrary, so exact plus anti-exact. So first, let's assume that j is exact form. So now you can decompose the phi into a homogeneous part, which solves this equation with j equal to 0, and inhomogeneous part, and apply the same method of the power series, and you get that inhomogeneous part have this form. So it's j, this j, which is acted on by h, and then there is this infinite power series of this operator. Of course, we have to check if this power series converges. So there are some, say, functional analysis conditions on the, say, norm of this operator, but generally it converges in some radius around this x0. Okay, and now general case. So j is generally arbitrary form. So exact plus non-exact, anti-exact part. So you can decompose it into three parts. So the first part solves this equation. So it solves the parallel transport equations where this current or this right-hand side is exact, because Ja is exact part of J, and this is exact because it's D something. Then there is the phi2 fulfills this condition, is algebraic conditions, and it's not always fulfilled because, for example, if you take, say, J equal these, well, if we have the space x, y, z in R3, then you can take something like this. dz is equal to dx times p2, and you cannot fulfill this because here's dz, this is dx, so you cannot compensate to get dz. So this is constraint which, if not fulfilled, this equation has no solution. So not always the parallel transport equation, general parallel transport equation, where j is anti-exact, has solution. Okay, yeah, and the third part is the kernel of this element, so it's introduce, in some sense, non-uniqueness to this solution. Okay. Okay. Of course, this operator has geometric motivation, so it should preserve the action of the group along the fiber. So we have to check if it's equivariant, or the solution of given by this operator is equivariant, or and also if it's horizontal. But it can be checked. We check it. So now some connection with Cartan, yeah, because it's a workshop about Cartan geometry. So for example, if you look on the first structural equation which defines torsion, so for example, assume that you know the torsion and you want to find this part, and of course you know the connection because you compute it from the second structural equation, knowing curvature. So this is exactly the form of the equation which I presented, because you know this omega, which is A in these previous slides, and T is J. Yeah, so you can solve it. And of course you can solve the second structural equation, because it's some kind of Riccati equation, and the solution of this equation was given in Edelman book. It's well, it's more complicated, but it can be done using this homotopy stuff. Okay, so now other applications. So the first one is that from the mathematical physics. So the Maxwell equation is D, large D acting on F is equal to G, where D is called Dirac equation, sorry, Dirac operator or Dirac-Haller operator, but it's on the, well, it's in this approach it's called Dirac. So if you plug this operator here, F is two form, J is a combination of one form and three form. Where in general it's one form. When it's three form, it means that you consider also magnetic monopoles, which doesn't exist, at least as we know. Anyway, you can also modify this using or adding more forms like 3 forms, 4 forms, and so on. And it's called P-form electrodynamics. And because of these operators are included in this equation, we can solve it using these homotopy operators. What is very interesting is that on Riemannian manifold, you have a Hopf star. So using this very nice property, which dualize, well, here we have multiplying by A, and if you apply stars, then you say switch this multiplication by A by inserting A sharp into this dualized phi. So if you apply star on this parallel transport equation, you get these equations. Well, there is a co-derivative, and here is insertion of this A sharp into phi. And you can, by dualizing all these results, get another way of solving the equation. And but you don't have to dualize, because you can define a cohomotopy operator, which is Hopf star dualized homotopy operator, and you can work with this operator. Okay, then you can also solve this equation. It's like second order differential equations, because you apply covariant derivative twice on phi, and is equals to some inhomogeneous term. And the solution is very simple. Like in ODEs, you split this second order covariant second order differential equations into the system of first order differential equations. So first you solve this equation, which you know already how to solve, and then you plug phi2 here and solve this equation. Okay, step-by-step solution. Okay. And you can generalize even more. You can define a lot of these say covariant derivatives with different one forms and anti-say or co-covariant derivatives with there should be some I index. So, and you can decompose these operators which acts on some unknown form phi, and it's equal to J. So I call it geometric-based differential equation because they are motivated from differential geometry. And how to solve it? So you can split it into the system of first covariant order differential equations and solve. For example, if you have this equation, then you switch to the system and solve it step by step. So first this one, and then plug phi2 here and solve this one. So nothing difficult. Okay, by the way, you can also try to apply this decomposition into exact and anti-exact part into in the variational calculus, but we tried, and the only thing which we found that this anti-exact part is responsible for non-variationality of the Euler form, or well, it's not called Euler form. So if you take differential equations and make Euler form, then you apply vertical derivative on this, and if it's 0, then the equation that extends is variational. If not, then it's not variational. And if it's not variational, it means that this original form was anti-exact. So that's only thing. And by the way, this formulation of the problem, we find out it's well, improper in some sense, because every equation is variational in some sense. But it's either variational, or you can reduce it from variational by Dirac reduction to the equation which is non-variational. So almost every differential equation is variational in this sense. Okay, so now how to connect it with operator calculus. So you work on differential operators which fulfills the following rules. So they are linear and they fulfills Leibniz rule. And that's typical definition for example, covariant derivative and normal derivative. But you can define differential operators in different way by looking of how they act on different operators. So for example, if you take differential operator, and the second operator is integral, so some local inverse to the differential, then acting of differential on the integral is identity, and acting integral on differential is identity minus something, which is the projection on the boundary. So because of this, there is no perfect inverse. So here's the proper way of how to generalize. It's called Bittner-Vettor calculus. So you define differential, which is operator which acts between two vector spaces. The integral is also operator which acts in opposite direction, but it depends on it's parameterized by the kernel of this differential. So you pick one element from the kernel and you define this integral or generalized integral, and also you have to have this projection on the boundary conditions, which takes element from L0 and projecting it to the kernel. And here are the properties of this abstract integral and abstract derivative. So S acting on T is I, and T acting on S is I minus this abstraction in some sense from the inverse. Okay, and if you look on action of the homotopy operator and exterior derivative, you can also find this structure. So L0 is the sum of A and anti-exact forms, and L1 is the space of exact forms, and H acts here, D acts here, and also D takes exact forms to the kernel, and H takes anti-exact form to the kernel. Okay, so here's also a summary of this. Yeah, so taking this homotopy invariance formula, you have this H, D is equal to identity minus something, and this something is exactly projection on the boundary, which for zero forms is this operator, and for non-zero forms is this operator. Okay, and summary. So as we have seen, probably as you know from the basic courses, the Poker lemma results from homotopy operator, and this operator, at least for linear homotopy, has very nice properties. I mean that it can be used to construct the projection on the exact and anti-exact forms, which can be used very effectively in solving differential equations in differential geometry. And also on locally on star-shaped subsets, you can solve almost any operator, any differential equation-based resulting from differential geometry using this approach. Yeah, and if you want global solution, then you have to match all these pieces and use some kind of topology. Yeah, that's usual approach to the differential geometry. So first you start from differential equation, you solve it locally, because differential equations can be solved only locally, and if you know more, then you can match everything and construct global picture. Okay, what is under work? So what is missing is effective solution of Einstein equations. Well, because Einstein tensor is not, say, you need something more. You don't need, well, you need the Lie algebra, but you need to take or go out from Lie algebra to Cartan, sorry, not Cartan, but Clifford algebra, and then you can construct Einstein tensor. Well, you can. Okay, maybe let's keep it as this. So you need some procedure which interacts between homotopy and Clifford algebra, just to make some efficient procedure to solve iteratively, I think, Einstein equation. Also, there is a problem with green functions. So if you have Laplace-Beltrami operator, then you can also try to construct a local inverse, which is called green function. But in this picture, using homotopy operators, we cannot do it yet. Well, there was one paper which, well, at least we try to say that they do it, but we try to check it, and there is some mistakes. At least we believe that there are some mistakes. So this problem is also open. Okay, thanks for our support. And so if you want to know more, then here's the very nice book, and of course our papers. And thank you for your attention.
So we ran over a little bit, so if there are any questions, let's keep them short. There are several.
Yeah, you said you can, with this method, you can solve the structure equations.
Yes.
For the Cartan connection. So does that mean you can construct, let's say, a connection to the given hologram?
Well, it's local.
Yeah, locally.
Yes. So you take a local subset like star shape, and you have curvature on this and torsion prescribed. So first, from the second structure equation, you take or you solve it by so you get connection form, and then you plug it to the first structural equation, and having torsion and connection, you can solve for these omega forms. Yes, well, you write it. So the first structural equation is something like this. Well, Jan wrote it on his lecture. So this is this translation part.
Yeah, sure.
Yeah.
Don't need a reminder.
Yes. So this part of this omega mu is torsion, and the second one is
Yeah, so let's say torsion is 0, and then you want to prescribe the curvature.
well, yeah. So
And that you can solve.
you have curvature, then you can solve for connection. And if you have connection, you plug it here. You have torsion, so you can solve for this. Yeah? So this is some kind of parallel transport equation. Well, if torsion is 0, then it's exactly parallel transport equation for these forms. And this is the equation for connection, which is similar to the Riccati equation in some sense. Anyway, it's the method of solving this equation is in this book. Yeah. So that's the algorithm for this.
I didn't understand. You start with ODEs, and of course, there's always like solutions, like
Yeah.
in the loop, right? But then you say you generalize and you can solve kind of any PDE.
Well, not any,
And
but
so I don't understand what kind of theorem you use to find, because you just given PDE, you write solution, even though there may be no solution.
yeah. Well, it all depends on the convergence of this power series. Okay, so if this radius of convergence is 0, then you don't
There
have.
may be no formal solution.
Yeah, formal solutions, yes.
It doesn't matter. Convergence or convergence.
Yeah,
There
yeah,
is no formal.
you can solve it. You know, locally, well, maybe not every, but many differential equations have solutions. And our method is not the first one, because sorry, that's the last slide. So there is a method of solving parallel transport equations from 1977. It's called Chern iterated integrals. The idea is as follows. So you take a curve along which you want to solve the equation. Well, generally you construct path space, and you pull back parallel transport equations along the path, and you get ODE, and you treat it as operator equation and solve it iteratively. So in the end, you get some operator series solution for this, but along the curve. Our method treats the full PDE and solves it locally in a star-shaped subset. So it's not like the only way how to solve parallel transport equation. This is other one, but it's different in the sense that it transforms parallel transport equation to the ODE. We use PDE locally. Yeah. Of course, you have to assume smoothness and so on. So there are some assumptions, but they are technical. Yeah. So that's more or less. I can explain you maybe later in details the procedure.
All right, let's thank the speaker one more time and call it a day.